Viscosity. The property of viscosity is describe the fluidity of the fluid. So viscosity is a physical property of fluid. It shows resistance to flow. In a simple example, water has a low viscosity as it is thin. However, for maple syrup has a high viscosity as they are thick. A way for test for viscosity is the speed at which the substance runs down a slope. Maple syrup would reach the bottom very slowly and water would be much quicker. So this statement is referred to the idea of if you have an inclined plane here, you could test the viscosity of a specific liquid. For example, if you put a water here, so it will reach the bottom plane here quicker compared to the maple syrup, because maple syrup has high viscosity, so it will flow down slower compared to water. Another method to test the viscosity is by stirring the liquid. So for water, it has low viscosity, so you could stir it easily. However, for maple syrup, so because it has high viscosity, so you may use a certain energy to stir the syrup. Now we would like to see the mathematical relationship that we could have if we have viscosity act in our system. Let's say we have this system. We have two plates. We have bottom plate and the top plate like this. So and then the bottom plate here, we fix the plate, so means that the plate is not moving. And then between these two plates we put a liquid. So and then we try to pull the top plate here with certain amount of force. So we found that if the liquid here has high viscosity, so if the liquid here is thicker, so we need more force to be used to pull the plate. So means that the molecule here, okay, the first thing that you need to understand here, the molecule that stick on the surface here will have one special phenomenon called no slip condition. So no slip condition means the molecule here will stick very hard on the surface and then it will not moving. It's not move, so it's called no slip condition. So and then because it is not moving, so the velocity u is equal to 0. So because it stick very hard, so means that it create a resistance to the plate. So means that if you want to pull this plate with certain force, so you need to overcome all the shear stress from this molecule before you could pull it with certain speed. So to measure or to calculate all the resistance force here, so we could use the idea of tau times A. So tau here is shear stress. So it is reflect the idea of one molecule here stick on the surface. So and then we multiply with A, which is A is the area. So the area of plate where the shear stress occur. Okay, so and then the tau A here will give us the total amount of force or the total amount of the resistance force. So in equilibrium, we could write that if we want to pull the plate, so this force must be equal or more compared to the force of resistance here. So in equilibrium, we could write force F is equal to tau A. Certain textbook, it will use capital P to show the force. However, in our class here, I would like to use F to represent the force. So means that in this situation, the mathematical relationship that we could have here is force is equal to tau shear stress times the area. So and then this idea is studied by Newton so many times ago. So and then Newton proposed the idea of the shear stress here is actually has direct proportion with the velocity gradient. So the velocity gradient means du dy. So this is the mathematical expression. So means that it shows only the relationship between the shear stress and the velocity gradient. And then to have a mathematical equation here, what we could do is, okay, so we create a graph. For example, we take the y-axis is tau and the x-axis here is the velocity gradient du dy. So and then we could make an experiment. So we have a force here, so we change the velocity of the force here. The velocity you pull the top plate. So and then when we do this experiment, we could plot the graph. Okay, let's say we could have a data of this one, and then finally Newton found that the relationship is a straight line. So when you get the relationship is in a straight line, so you may have y equal mx plus c. So and then the c here is equal to 0 because it starts with from the origin of 0, 0 here. So and then the gradient here is actually the value of mu. That's why Newton proposed the shearing stress and the velocity gradient can be related with a relationship of this one. Tau is equal mu du dy, where tau here is the shear stress, du dy is the velocity gradient, and the mu here is actually the gradient of this line. So this mu is called the dynamic viscosity. So the mu here is a dynamic viscosity, and in some textbook the dynamic viscosity also called as absolute viscosity. So the unit of absolute viscosity is shown here, kilogram per meter second, or Newton second per meter square, or Pascal second, or poise, or center poise. So the relationship between Pascal second and poise is shown here, which is 1 Pascal second is equal to 10 poise. So and then we have another type of viscosity which named the kinematic viscosity. Relation between dynamic viscosity and kinematic viscosity can be written as this one. Mu is equal rho times nu. So this is mu, the dynamic viscosity. So this is rho, the density of the liquid or the density of the fluid. So and then this is nu. So nu here is the kinematic viscosity. So the unit for kinematic viscosity is meter square over second, or Stokes, or centistokes. So the relationship is 1 meter square per second is equal to 10,000 centistokes. Here I would like to explain to you about the velocity profile. The velocity profile indicates the magnitude of the velocity as a function of position. In this course, we are focusing in flow on flat plate and flow in pipe. A major feature of the velocity profile is the no slip condition at the surface. That is, the velocity goes to 0, which is v is equal to 0 at the surface. So this explanation, it is about as I said previously. So let's say we have a two plate like this. So we have a molecule here. So this molecule of fluid stick very hard on the surface. So because it is not moving, so means it's not slip. So we call the condition for this one as no slip condition. So and then the velocity here is equal to 0. It is because the outermost molecule of fluid is stuck to the surface past which it flows. In the other word, fluid molecules stick very hard on surface and give velocity equal to 0. So this is the justification of no slip condition. Particles close to a surface do not move along with a flow when adhesion is stronger than cohesion. At the fluid-solid interface, the force of attraction between the fluid particle and solid particle, adhesive force, is greater than that between the fluid particle, which is the cohesive force. The force imbalance brings down the fluid velocity to 0. The no-slip condition is only defined for viscous flow and where continuum concept is valid. So this is the example of velocity profile for flow in pipe. So for example, we have a pipe wall here at the top and at the bottom. So the velocity at the wall here is equal to 0 because these molecules stick very hard on the surface. So and then another molecule will travel in certain velocity. So and then at the middle, at the center line here, the velocity in the pipe will reach its maximum velocity. So and then we could draw the velocity profile like this. So mean it starts from 0, so it becomes maximum in the middle, and then it goes to 0 at the end of at the next end. So and then if we look the velocity distribution from the side view, so this is the side view. So we found that the pattern is like this because the pipe here is in circular shape. So and then boundary layer not only occur inside a pipe, it can be occur on thin plate. So this is the example where, for example, you have a very thin plate here. So and then the free stream velocity comes from left to the right. So and then it will go through on this flat plate like this one. However, because the fluid is stick very hard on this surface, so it gives us u equal to 0 condition, where the molecule is not moving, the velocity is equal to 0. However, the molecule after this molecule, the second molecule here, can move with a certain speed, because the interaction of that molecule is not solid surface to the molecule. It is between two molecules of fluid. So and then the next molecule will move with a little bit higher velocity and so on. So until one level, we found that the velocity reached its maximum velocity because it already reached the maximum velocity. So the next molecule here will also move with the maximum velocity. So we could draw the velocity profile here like this one. So mean it start from 0. So and then it increase a little bit, okay, until it reach the maximum value, and then the velocity start to constant to become. So and then that's why in certain application we draw the velocity profile as this one. Fluid for which the shearing stress is linearly related to the rate of shearing strain are designated as Newtonian fluid. fluid for which the shearing stress is not linearly related to the rate of shearing strain are designated as non-Newtonian fluid. So here the description between Newtonian and non-Newtonian fluid. So it is easy for us to understand according to this graph. If we do experiment with y axis here is the shear stress and the x-axis is the velocity gradient. If we do the experiment and we could plot graph between tau and du dy, so if the graph is in linear form, means in straight line, whether it has a very small angle here or it has a very big angle here, it doesn't matter, as long as the result, as long as the line is straight and start with a 0 0 here, so we call that liquid or that fluid as a Newtonian fluid because it has a straight line here. So what is the physical meaning of the straight line in this graph? So it shows that the gradient here is constant. So the gradient means the value of mu, dynamic viscosity, is constant at any condition. So this is another definition for the Newtonian fluid. So and then if it is non-Newtonian fluid, what happens? So you will have a curved line like this one, or you have a curve like this one, or you have curve like this one, or you have a straight line but it's not start from origin 0 0. So for this one, we call this line or this behavior as Bingham plastic. So it is example for molten metal. For example, we could analyze the molten metal flow into the molding, okay, by using the idea of fluid, but we need to modify the equation because it is not 100% similar with the fluid. So and then because it is non-Newtonian fluid, so maybe the viscosity keep changing, so it will influence the motion of that Bingham plastic. So in our syllabus, we not focusing on Bingham plastic, but we focusing on Newtonian here, a straight line, and the non-Newtonian liquid or fluid, which is can be divided into two types, which is shear thinning and shear thickening. So what you need to understand about shear thinning and shear thickening is, okay, for shear thickening here, so we found that, for example, at this moment, at this condition, so we could draw a line here and then we could get a gradient, and then at this line, so we could draw a tangent here and then we could draw a triangle. So here we found that at the moment means when the velocity gradient is higher, so the value of gradient here is become higher. So it means that the dynamic viscosity will increase itself when the velocity gradient is higher. However, for this curve, okay, at this for example at this point, so we will have a gradient like this, but for this one we found that the gradient is become smaller. So means that if the velocity gradient is increased, so the dynamic viscosity is become lesser and lesser. Shear thinning. So in fluid mechanics, shear thinning is the non-Newtonian behavior of fluid whose viscosity decrease under shear strain. Modern paint are example of pseudoplastic material. When modern paint are applied, the shear created by the brush or roller will allow them to thin and wet out the surface evenly. Once applied, the paint regain their higher viscosity, which avoid drips and run. Okay, ketchup is a prominent example of a shear thinning material, being viscous when at rest but flow at speed when agitated by squeezing, shaking, or striking the bottle. Whipping cream is also an example of a shear thinning material. When whipped cream is sprayed on when whipped cream is sprayed out of its canister, it flows out smoothly from the nozzle due to the low viscosity at high flow rate. However, after whipped cream is sprayed into a spoon, it does not flow, and its increased viscosity allows it to be rigid. And about shear thickening. A shear thickening or dilatant fluid is one in which viscosity increases with the rate of shear strain. This can readily be seen with a mixture of cornstarch and water, which act in counterintuitive way when struck or thrown against a surface. Sand that is completely soaked with water also behaves as a dilatant material. This is the reason why when walking on wet sand, a dry area appears directly underfoot. Now I would like to share with you the idea how to measure a viscosity. A viscometer is an instrument used to measure the viscosity of a fluid. Rotational viscometer is usually used to measure a dynamic viscosity. It has mechanism as shown here. The more viscous a liquid is, the higher the force required to rotate the pedal. This torque value will be recorded and calibrated to obtain the dynamic viscosity value. So the idea is very simple. If we have a shaft here, and then this shaft is connected with a certain device, or in this picture we have a pedal here, and then we rotate the rotor here with certain force, with certain torque. So we found that if the liquid inside this container has high viscosity, so means that this machine need more power to rotate at specific velocity. So by using the difference between the force that we need to stir or to rotate here, so we could calculate the dynamic viscosity for that liquid. So, and then we have another type of viscometer. It's called a glass capillary viscometer. A glass capillary viscometer or Oswald viscometer is usually used to measure the kinematic viscosity. So here in this device, so we have a rotational device, and it only measure the dynamic viscosity. But however, for this device, so it is measuring the kinematic viscosity. The time required for the test liquid to flow through a capillary of a known diameter of a certain factor between two marked points is measured. By multiplying the time taken by the factor of the viscometer, the kinematic viscosity is obtained. So the idea is simple. So we have a vacuum pump here, and handheld vacuum pump. So we suck the liquid until this level, and then we let it flow gravitically. So only by use gravity acceleration. So and then we need to measure time when it move from this point to this point. Okay, so and then the time taken, okay, will be referred to a special table, and then we could get the kinematic viscosity from that table. The more viscous a liquid is, the longer it takes for the liquid to flow from the start mark to the stop mark. This time value will be used to calculate the kinematic viscosity value. Often, the value of kinematic viscosity can be obtained from a table prepared based on the time taken. So means this device has its own table, and previously the manufacturer will calibrated the calculation. So you take the time, and then you refer to the table, refer to the specific table, and so on. So and then you will get the value of kinematic viscosity. Another example of a viscosity that commonly used in our daily life is the engine oil. I think all of you has your own transportation. At least you have a motorcycle or a car, and then for to run the engine, so we need lubrication. So we call it as engine oil. So, for example, if your engine oil classified as 10W50 is a heavy-duty multi-grade oil craft to support an engine maximum performance at a very high operating temperature. So what is its mean? So it means that engine oil is actually, as you know, the combustion occur and the temperature is very high on the engine. So we need to make sure that at high temperature, the viscosity of engine oil is remain in certain range. Because previously in our class here, we found that even viscosity of water, normally viscosity of oil will become lesser and lesser in high temperature. So if the engine oil is very thin, so means it cannot lubricate the contact surface very well, so it will lead to the engine failure. 10W50 follows the Society of Automotive Engineers SAE format for a multi-grade oil where W stands for winter. So this is the idea. The idea of W is, you know, when the temperature become lower, so the viscosity will become higher and higher, and in certain area in the world, if you have a worse winter season, so maybe the oil will become frozen inside your engine. So this will be, so means that it cannot flow anymore. So the number preceding the W, okay, denotes the oil flow at 0 degrees Celsius. The lower this number, the better the W oil will perform in winter. By not thickening, mean by not increase the viscosity. The number after W, 50, stand for the viscosity ranking at peak temperature. The higher this number, the better is the oil resistant against thinning at high temperature. Meaning 10W50 motor oil act like an SAE 10W weight under 0 degrees Celsius, and as SAE 50 weight engine oil at 100 degrees Celsius. So this is the range of temperature for certain example of engine oil. So I think you know our engine oil can be divided into three types. One is a mineral oil base, so means we use the petroleum base. So and then we have a semi-synthetic, so means that we modify the oil chemical chain and so on, but it is not all of them, so it's still in semi-synthetic, mean only half of them. And then for high performance car and so on, so we need the synthetic based engine oil, so means that we modified all the chemical chain to suit with the high performance engines. If you could see here, for synthetic based engine oil here, it can be used from negative 35 degrees Celsius until plus 35 degrees Celsius here. So this is the relation for SAE 10W40. So we found that at low temperature, so the kinematic viscosity is here. So and then at high temperature here, so the kinematic viscosity reduced, but the difference is not so obvious. So this is important to make sure that the engine could work properly with good lubrication all along the time.